Tutorial, I will solve some questions related to the entropy and free energy changes in chemical reactions and non-standard states. I will also solve some questions related to galvanic cells and in general electrochemical cells. So let's first begin. The standard free energy change delta G refers to the free energy change under non-standard. No, because the one under non-standard, it would be without this sign. The free energy changes under standard conditions, and the standard conditions are 1 atmosphere, a temperature of 25 degrees Celsius, 1 atmosphere for gases, and if I have solutions, it will be 1 molar. It's not enthalpy, and it's not... that's the meaning of delta G. It's the energy available to do work. But as a representation, we refer to it as the free energy change, the Gibbs free energy change. Again, as a definition, standard free energy change, it's the change in the Gibbs energy for a reaction occurring under standard conditions. It's the energy available to do work. So it's after whatever change that happens, the remaining energy is the one that's gonna drive a reaction. And what happens, this question is helpful whenever you get a change in an equation and they ask you to calculate delta G. So for example, if I have equation A plus B giving AB with a delta G standard of minus a value, let's say minus 70 kilojoule. So what will happen to delta G when the reaction is reversed? So if I say AB gives A plus B, the delta G is going to be now positive. We reverse the sign. What if we say 2AB gives 2A plus 2B? The delta G now is going to be multiplied, and that is 140 kilojoule. Now, if you have two equations and you are combining them, you will combine their delta G's. Like, for example, I have also AB plus D gives ABD with a delta G of, let's say, plus 100 kilojoule. Okay, so if I combine these two equations, I'm gonna get A plus B plus D gives ABD, and the delta G would be the sum of the negative 70 and the 100 kilojoule. Now moving on, which of the following is not valid for calculating delta G? Now this formula is always given to you in the exam. You have a formula sheet, so you have to look at the formula sheet. This formula is given. It's a valid formula to calculate delta G. Using only the enthalpy change of the reaction. If I use only the enthalpy change of a reaction, which is the sum of the enthalpies of formation of products minus the enthalpies of formation of reactants, this is a step, but it will not let me calculate delta G. I need delta S as well. So having enthalpy change only, not enough. Summarizing the standard Gibbs free energies of formation of products of reactants, yes, and they mean by this, if this is delta G, yes, we can calculate delta G, and combining delta G of components of reactions using Hess's law. So the one that is not a valid method is this one. Now here's a question to calculate delta G. So we have a reaction and we have a given. The formula is delta G equal delta H minus T delta S. You have to be careful that the delta G will always be calculated in kilojoule. Now if this equation is per mole, so we're going to put per mole. Now, delta S is never given to you in kilojoule, so you have to divide it by 1000 and make sure the temperature is always in Kelvin. So the answer would be minus 483.6 minus the temperature 298 Kelvin and the entropy 163.2 divided by 1000. So the answer is going to be minus 532.2 kilojoule per mole. So now when we look at the sign of this delta G, it's a negative one. So there is 532.2 kilojoule energy available to do work, to drive a reaction. However, if we move on to the next question, not all this energy available is going to do work. Some of it will be lost. So why not all free energy available to do work? All of it. Because some of this free energy will be lost as heat to increase the entropy of the surrounding, or some heat lost in the system. So we always have this. What's the difference between delta G standard and non-standard? So delta G standard, you will see this sign on it. So this is at standard conditions. And at standard conditions, it means the pressure for gases is 1 atmosphere. The temperature is 298 Kelvin. And if I have solutions, they will be at 1 molar. In the non-standard, you will see in the question they are giving you, for example, different pressure of the gases at the equation. And you will not have K, you will have Q. The equilibrium or whatever will be shifted. It will not be at equilibrium. So you will see that they are mentioning that we have different temperatures for gases. Now, so next, express the equilibrium constant in terms of delta G and RT, and use this relationship to estimate the magnitude and K and the thermodynamic favorability of the process. When you are given those graphs to determine where is the equilibrium, or where are we from the equilibrium, you just have to understand this. So if a graph is shifted toward the left, so here this is the lowest point of the graph, and this is where we have equilibrium. This is where delta G is equal to 0, and we have equilibrium. So this one is shifted more to the left. It means that this reaction is spontaneous. There is a free energy available to do work. And now, if the equilibrium shifts toward the right, it means this is the minimum energy that we still need so that the reaction can start becoming spontaneous. So I hope I can draw it like that. So here, the reaction right now is not spontaneous. So it's just we have to understand the value of delta G and what does it mean. So if there is energy available to do work, or if this is the minimum required energy we need to start a reaction, to start doing work. Okay, so the larger the delta G far away from equilibrium, it means that if it's in the negative, this is a lot of energy available. And if it's positive, it means that this is how much we still need. Now when delta G is 0, we're done. There is no more energy available to do work. Which of the following statements is true about equilibrium constant for reaction when delta G is negative? When delta G is negative, that means the reaction is spontaneous. The K would be over the more than 1. We never say K less than 0 or negative or positive. It's either above 1 or below 1, because K is always representing values of products over over reactants. So if this is over 1, it means that this reaction is shifted more toward the product than toward the reactants, meaning that it is spontaneous. Now, let's move on to the questions where we apply Hess's law in calculating delta G. Whenever you are looking at questions like these, follow this technique by checking where to find each substance in the given equations. So I'm gonna name this equation A, B, and C. So first, start finding and looking for carbon solid. It's in equation B. Carbon in the given equation is in the reactant, and it is multiplied by 3. In B, carbon still is in the reactants, but we need to multiply it by 3. So we decide that B, we will not flip it, only multiply equation B by 3. So this means we are going to multiply the delta G as well. So therefore it's going to become 3C plus a 3O2 giving 3CO2. And we're done with the 3 carbon. Now let's find hydrogen. Hydrogen, we can find it in equation C. And we need it to be multiplied by 4 instead of 2. Because here we have 4. So we're not going to flip equation C. We are only going to multiply equation C by 2. Therefore, the delta G will also be multiplied by 2. So let's copy it again. 2 times 2, that's 4 hydrogen plus 2 oxygen, giving 4 H2O. Now we're done with this. C3H8, we finally find it in equation A, but we need it to be with the products. So we decide to flip equation A, and that is going to be 3CO2 and 4 H2O to produce C3H8 and 5O2. And when we flip an equation, the delta G becomes positive. Now, after changing the equations that I named A, B, C, now we need to add them all. And when we add them all, we can check that they are giving us the required equation. It means that what we did is correct. 3O2 and 2O2, both of them being in the reactant side, equal to 5O2. And I have 5O2 on the product side, so common substances will be cancelled. 3CO2 product side and 3CO2 reactant side will be cancelled because they are common. So I'm going to cancel them. Same thing for 4H2O will be cancelled. So what remains is 3C, the way we want it, and 4 hydrogen, giving C3H8. Then we're right. And now we proceed to add the delta G's. So 2074, and I have negative 394.4 multiplied by 3, that is 118 3.2, and I have another one, 457.1 multiplied by 2, that is a 914.2. So I add them all, and the final answer is 23.4 kilojoule. Next, given the following equation, dinitrogen monoxide, nitrogen dioxide giving 3 nitrogen monoxide with a delta G. Calculate the following, the delta G for the following one. What did they do over here? They simply flipped the given equation. So the delta G will be, we will flip the sign. Only flip the equation. So we are going to flip the sign. So this is given as negative. I'll write it as positive. What was spontaneous reaction? If it's written in this way now, it's going to become non-spontaneous. But what if this same given equation, now the same one is now multiplied by 2? What will be the delta G? I will simply multiply now the 23.0 by 2, and that is 46 kilojoule. Again, using Hess's law, calculate the delta G of the following using the following information. So as I'm telling you, you search and you look for, the substance. So CO, where can I find it? I'm going to change the color or make it faint. So this CO, I can find it over here. I have it in the right place as a reactant and with the same coefficient. So do nothing to this equation. So equation A and equation B, I'm not going to do any changes for B. Now, carbon solid is over here. Also, it's in the A and nothing to be done. So nothing to be done to A, nothing to be done to B. So simply, we are going to add them. So CO2 from this side and CO2 from this side, because they are common, they cancel out. So I have carbon monoxide gas. Now, I have half molecule of O2 versus 1 O2. So here remains half oxygen molecule and the carbon solid. So the final delta G will be adding these two values, and that is equal to 137.2 kilojoule. Now, another way, using the summation method and not Hess's law. So here you have an equation, and they are giving you the standard free energies of formation of the substances on the equation. So you need to use it. One common mistake that the students do, they get confused between product side and reactants side. So product side, you have to start with them minus the summation of the reactant sides. So let me just go back and do the product side. I have CO2, I have H2O that I need to multiply by 2 because there's number 2 over here. And I have O3, which is over here, and I need to multiply it by 4. All of these, we add them together. So these are the summation of the enthalpy, the Gibbs free energy of products, their sum. So it is equal to negative 394.4 plus 2 multiplied by negative 228.6 plus 4 multiplied by 163.2. Now, let's do the reactants now. the reactants, I have CH4 50.5 and I have 8O2. You need to show it on the equation. Even if it's 0, you still need to show it on the equation. So the summation of the Gibbs free energy of reactants is the negative 50.5 of CH4 plus 8 times the 0. So that is negative 50.5. Now, the final answer, the delta G of formation, the delta G of the formation of this reaction is the products, and the value over here is equal to we have 4 multiplied by 163.2 is negative 198.8. So negative 198.8 minus the reactants, and the answer is going to be negative 148.3 kilojoule per mole. Now moving on to another question. Calculate the delta G standard at 25 degrees Celsius. Remember, we never leave the temperature in Celsius. We always add 273 to it to become in Kelvin. Determine whether the reaction is thermodynamically favored or not. So they're telling you just find delta G, whether it is negative or positive. Now, this is a long process because I don't have delta G. I have the enthalpy of formation and I have the entropy of these substances. So we're going to use this formula, minus T delta S. Okay? However, we need to find this first and we need to find this separately as well. So let's start with the enthalpy of formation, and that is the enthalpy of formation of product minus the enthalpy of formation of reactants, their sum. So it is negative 100.4 minus negative 120.9 and 105.9. And the answer would be minus 85.4 kilojoule per mole. Now let's find delta S using the same way. So delta S is going to be as well the product. I'm going to use the same color. Product minus the two reactants. So 107.1 minus the sum of 73.93 and 80.71. And the answer is going to be negative 47.54 joule per mole Kelvin. We have to be careful not to forget the step of converting entropy to kilojoule per mole Kelvin. Now, finally, let's find the delta G. Delta G is going to be enthalpy. I'm applying this formula. So, enthalpy is this value minus 85.4 minus the temperature that I have it at 298 Kelvin multiplied by negative 47.54 divided by 1000 to convert it to kilojoule. And the answer is going to be minus negative 71.23 kilojoule per mole. So this delta G is negative. So the reaction is thermodynamically, yes, it is thermodynamically favored. Now, let's look at, again, let's just, for the sake of the question B, let me just put what we got. We got a negative delta G, we had a negative enthalpy, and a negative entropy. So basically, this reaction is thermodynamically favored in condition that the temperature is low. And obviously, the right temperature right now, 298, is a low temperature. So the next question is saying, estimate the value of delta G reaction at 125 degrees Celsius. They increased the temperature. T is increased. We were doing our calculations at 25 degrees Celsius. If temperature is increased, the reaction is going to become less favored. But if the temperature was decreased, the value of delta G is going to become more and more in the negative. So it's going to become more and more thermodynamically favored. So simply, the answer to this question, it's going to become less thermodynamically favored. Since delta H and delta S are both negative, this reaction becomes more and more favored whenever we lower more and more the temperature. Now, moving on. Consider the reaction 2NO plus O2 giving 2NO2. Be careful of these questions. The standard, the Gibbs free energy standard is already given. And you will notice in this question that they gave you pressure of these gases. It means that in this question we are dealing with non-standard conditions. So they just want to know that if the reaction is going to be more or less thermodynamically favored with the given conditions. In order to know that, we need to use a formula of delta G, the new Gibbs free energy at non-standard conditions. And this Gibbs free energy is equal to the standard plus RT ln Q. I'm sorry. Here you need to be careful that it's a long process of calculations. We need to calculate first Q. And by the way, this formula is not given to you in the AP formula sheet. What's given in the AP formula sheet is the delta G standard equal minus RT ln K. So be careful. Here, when you plug it into the formula of delta G, this sign becomes positive. It's as if you are taking all of this to the other side. So it becomes positive. And it's Q, not K. So let's split this equation and calculate part by part. So first, I'm going to start finding Q. Q will take the formula of K, which is the pressure of product raised to the stoichiometric coefficient. So the pressure of NO2 squared divided by the pressure O2 multiplied by the pressure of NO raised to their stoichiometric coefficients. So the pressure of NO2 squared multiplied by the pressure of O2. Okay, so that is equal to 2 squared divided by 0.1 squared multiplied by 0.100. And the answer is 4,000. We don't know whether we skipped equilibrium or not. Now, In this condition, temperature is given to us, it's in Kelvin. Now R, you will find it given to you in your formula sheet. The formula of R, the value of R is 8.314 joule per atmosphere, per Pascal. So it is and mole Kelvin. So basically it is in joules. So you need to convert it to kilojoule. So now let's plug it into our formula. Delta G non-standard equal the standard delta G plus R divided to convert it to kilojoule multiplied by the temperature 298 Kelvin multiplied by the ln of 4000, and the value is going to be negative. So the reaction is still favored, but it was negative 70. Now there is less energy available, so it is less favored under these conditions. Moving on, in the Haber process, find delta G of this reaction. The standard is given as negative 33. The value of delta G at 298 Kelvin for reaction mixture that consists of 1.9 atmosphere of N2. So here they gave us new pressure. So just like the previous question, they changed the condition of pressure. So we still need to calculate Q, and that is the pressure of ammonia squared divided by the pressure of N2 and the pressure of H2 cube. So Q is equal to NH3, it's 0.65 squared over N2 is 1.9 and H2 is 1.6 cube. So once we find Q, we plug it into the formula of delta G non-standard is equal to the delta G standard plus, so the delta G standard is given over here, negative 33.3 plus R. As I mentioned, I need to divide it by 1000 multiplied by the temperature, that is 298 Kelvin, multiplied by ln Q, and ln Q is this value. So 0.65 squared divided by so it is 0.054. Anyway, when we plug this into the calculator, we're gonna get the choice. Continue. Another question. Which of the following is true? If delta G is positive, there's no way K to be over than 1. If it's negative, it's the opposite actually. Delta G is 0 at equilibrium. Yes, that is correct. Delta G non-standard is 0 at equilibrium. No, because when we are at equilibrium, we have standard, we don't have delta G. The correction to choice D could be at equilibrium, delta G non-standard equal equilibrium. That's it. Okay, so we cannot take choice D. Because there is no non-standard when we are at equilibrium. So the answer is C. What is the value of delta G standard if K or Q is given? So I can do something. We are at equilibrium. So we're dealing with equilibrium. That's why they wrote K. Having K more than 1, so definitely the reaction is spontaneous. I can eliminate A and D. Now I just need to do my calculations in order to find the value. So minus 8.314 over 1000 divided by, multiplied by the temperature in Kelvin, once I convert it to Kelvin, multiplied by ln K. So plugging this into our calculator, we'll find choice C to be the answer. Some more questions. I'm gonna move a bit faster. So calculate delta G. Use the value of delta G, to calculate the equilibrium constant K. We are always dealing with delta G in standard conditions. So we will be using this formula provided to you in the formula sheet. So see here, I write K and not Q. So how to find this? Having delta G equal minus R divided by 1000 multiplied by temperature converted to Kelvin multiplied by ln K. When you plug this into your calculator, you can do solve for X, and the calculator is going to give you a value of 6.87 times 10 to the power of 5. It's a very large value, which is consistent with the given delta G is negative, so logically K is going to be a large value. Now we continue. I need to calculate, use the free energies of formation given over here to calculate K of this reaction. So I don't have delta G reaction. So first I need to find delta G reaction. And I'm going to take products. Of course, you multiply it by the coefficient minus the reactant. So first, delta G of the reaction standard is the sum of the Gibbs free energy of product minus the sum of the Gibbs free energy of reactants, and that is equal to by 51.3 minus 99.8, and the answer is 2.8. Okay, that's not a standard, that's not a favored equation, kilojoule per mole. So my expectations to obtain K 0 point something, a negative, a less than 1 value. So let's plug this into here. 2.8 equal minus 8.314 again divided by 1000. The equation is happening at 298 Kelvin ln K, and you do solve for X, or you can use it this way. So the K here is going to be 0.323, which is a logic answer. One more time. Now, using a different formula, we want to calculate K. Here we don't have yet delta G, the Gibbs free energy, so we are going to use this formula. Since these are given, we find delta G, then we plug the delta G into this formula to find the equilibrium constant. So minus 304.2 minus the temperature is 498 multiplied by S, the entropy, divided by 1000. So the answer of this one is negative 97.93 kilojoule. Now let's use the second formula. This 97.93 is going to be equal to negative RT ln K, and the temperature is 498 and ln K. Plug this into your calculator. Since delta G is a negative value, I expect K to be a large number above 1. And indeed, after we do our calculation, it is 1.8 times 10 to the power 10, raised to the power of 10. Okay. Another question to calculate the delta G of this reaction by using 3 given equations. So equation A, equation B, and C. So let's first find each one. N2O, I can find it over here. I have it in the reactant side, but I need to get rid of this 2 next to it. So I decide that equation C to be divided by 2. So that is going to be N2O gives N2 and half O2. And the delta G is going to be divided by 2. So the answer is going to be negative 103.7 kilojoule so far. So we're done with this. Now I need NO2. Now NO2 is over here. I need to flip A and remove the 2. So we need to flip and divide by 2. So I'm going to flip. I'm going to start writing here NO2, and I divided by 2 will give me NO, because we divided by 2, plus half O2. As you can see, half O2 and half O2, in the last step, we're going to add them together. So when this is flipped and divided by 2, the sign is going to be like that, positive and over 2. So the answer is positive 35.6 kilojoule. We're done with this. Now let's look at NO. NO, I can find it in equation B, but also I can find it in equation A. So I have to be careful. So we need to have a 3NO. We already have 2NO in B, and we have 1NO from equation A. So that's it. We do nothing to equation B. We just copy it. And adding the 2NO and the NO is going to give me 3NO. So I'm done with it. And I have here half O2 plus half O2, that is 1 O2, and 1 O2 from this side common will be cancelled. Same thing, N2 and N2 will be cancelled because they are present at opposite sides. So the final equation is N2O and NO2, giving this one. So exactly as expected. So the final delta G of this reaction is going to be the summation of the 3. So 35.6 and 175.2 and negative 1.3.7. So the answer is C. In the reaction A to B that has an equilibrium constant less than 1. So if K is less than 1, we expect delta G to have a positive value. So what is the value of the reaction? Done. Now again, delta G given to us positive. It means that it is not favored. And when it is not favored, K is less than 1. So K is less than 1. So I'm going to omit the options A, C, and E. Now let's read. Here they want if the reaction favors the formation of reactant or product. If it's not favored, it means that it is favoring the reactants, not product. So B. Here's a question. There was a mistake in this question and I corrected it. So I have again 3 given equations, A, B, and C. So Hess's law is a very common question to be given in exams. Okay, we need to first look for CH4. So we need to use these 3 given equations in order to find the enthalpy change of this below equation. So first of all, CH4, where is it? It's in A, and I need it to be having here 2. So I need to multiply all equation A by 2. So if you look at the answer, this is a multiple choice answer. They just want to find out the new delta G in form of X, Y, and Z. So I'm multiplying all A equation by 2. So X is going to be multiplied by 2. Next, 3 half O2. 3.5 O2. So first of all, I have here 2 O2 from equation A, and I need to multiply either B or C by 2 in order to have 3 O2 and a half. Now this is going to be a bit confusing. So because I have O2 in equation A, B, and C, so I can skip this part and move on to another substance that is not found in different equations and decide what should be done to B and C. So looking at here, this formula, COOH2, it is found in C, and it has a stoichiometric coefficient of 1, it means that we are not going to multiply C by anything. So that's it. I'm going to leave it. So keep C as it is. Okay, so it's gonna remain as Z. Now, looking at here 3H2O, I have 2H2O from A and I have 1H2O from C. That is 3H2O. But still, the O2 molecule is not fixed yet. As I told you, we need 3.5. So this is 2. And we decided not to do anything to C. This is the half. I need 1 more O2. Therefore, I need to multiply B by 2. Or you can think about it in a different way. You can look here and see that I have HCOOH and I have 2 HCOOH. And in the given equation, I shouldn't have this one, formic acid, HCOOH. So I need to cancel this one. So we need to multiply equation B by 2 in order to cancel this substance. So 2, and that is now 1, and here is 2. So these are cancelled. And the equation is going to be 2y. And here we go. We have 2HCHO and 2HCHO from this side. We're done. 2H2O and 1H2O, that is 3H2O. 3.5 O2. So the final answer, after we do the changes to equation A, B, and C, we need to add them up So the final delta G of this equation is going to be 2x plus 2y and z. That is C. And finally, the last question in this lesson. Which of the following is true for a substance undergoing the change given below at the normal boiling point? So we are at equilibrium. And at equilibrium, because they said normal boiling point, that's why. So at equilibrium, delta G reaction is 0. We are at equilibrium. Now, knowing that delta G is equal to delta H minus T delta S standard, it means that if I put 0 over here, I can take this value to the other side and I'm going to get T delta S equal delta H standard. So that is the answer. Now, moving on to electrochemistry. Which of the following is the correct first step in balancing a redox reaction in an acidic medium? I mentioned in a previous video how to balance redox equations, and it's very important that you follow the steps in the same correct order. So first you balance all the atoms that are not oxygen and not hydrogen. So balance atoms, not O, not H, by adding coefficients, by adding stoichiometric coefficients. And then you balance O by adding H2O on the side that is missing oxygen. Then you balance the hydrogen by adding H plus on the lower side. Finally, you balance the charge by adding electrons on the higher side. Once this step is done, you look at the electrons lost and gained in both equations and you balance them. So, the correct first step in balancing a redox reaction, you balance oxygen by adding H2O. True, but that's not the first step. Oh yeah, you're right, the oxidation, you split it, of course. You split the oxidation and reduction half equations and then you start balancing atoms. So this becomes step 1. This be step 3, because there's step 2 to balance the atoms, step 4, and step 5. Next, okay, let's look at this example. I'm gonna go with you step by step. So here's a given equation. So first of all, split it into two half equations. And by splitting it into two half equations, Fe2 plus gives Fe3 plus, and MnO4 minus gives Mn2 plus. So I'm gonna start Fe2 plus. Never forget to write the stoichiometric coefficients. The physical states, I'm sorry. So these are the physical states. You can leave them till the end of the equation. Now, step 1, I split this redox equation into two half equations. So let me now focus on this one. Balance atoms, which is the Fe. 1 Fe, 1 Fe, the atoms are balanced. Balance O by adding H2O, there is no O in it. Balance H by adding H plus, there is no H in it. So we reach the part where we balance the charge. So on this side, I have a +2 charge, where here I have +3 charge. So I will add electron on the higher side, it means on this side, and I want the 3 plus to drop to 2 plus. So I need to add 1 electron on the higher side. So this is the oxidation half equation. Okay, now next I'm gonna then the other one definitely is going to be the reduction. I'm going to start balancing the half reduction equation. 1mn, 1mn, balanced. 4O, so I need to add H2O on the side that is not having O. So I cannot add H2O over here. I need to add 4 H2O on the side missing oxygen. Now next, by adding H2O, you now have 4 times 2, 8 hydrogens on this side, whereas on this side, no hydrogens. So you balance H by adding H plus on the side missing hydrogen. Now, we reach the part where we balance the charges. Let's first count the charges. On this side, I have 2 plus because 4H2O has no charge on it. It's neutral. Whereas on this side, I have 8 pluses. Don't forget to multiply it by 8. 8 pluses and 1 minus. So that is 7 plus. So I need to drop the 7 plus to 2 plus. This is the higher side. So I am going to add 5 electrons on the higher side to drop the 7 plus to 2 plus. So plus 5 electrons. So here we go. Now, finally, after finish balancing the half oxidation and the half reduction, we now need to balance the charges. Here I have 1 electron lost and 5 electrons gained. So we will multiply the first one by 5. So 5, and we add them up. 5Fe2 plus MnO4 minus and 8H plus. Of course, I can't forget the AQ. Will give me Mn2 plus and 5Fe3 plus aqueous and 4H2O liquid. And that is the final balanced equation in acidic medium. Again, another example. Balance the reaction. Again, I'm going to split it into 2 half equations. NO3 minus giving NO2. I can suggest that you pause the video and you do it yourself and then you compare. And the other half is I minus giving IO3 negative. So these are the 2 half equations. First of all, balance n atoms 1 by 1. It is balanced. Balance O by adding H2O on the lower side. I have 3O2 and I have 2O2. So I just need 1 more oxygen. So I add H2O. Now, I have 2 hydrogens on this side and I don't have hydrogens on this side. So I'm going to add 2H plus on the side missing hydrogen. Now I reach the part where I balance charges. Obviously, on this side, there are no charges. So the charge is 0. And on this side, I have 2 plus and 1 minus. So that is 1 plus. So 1 plus, I want to drop it to 0. What do? I simply add 1 electron. And that's it. I finished balancing the first reduction half equation. Now for the second one, 1I balanced. 3O, and there is no O on this side. So I add 3H2O on the side missing oxygen. Now, by adding 3H2O, I now have 6H plus. So I need to add 6H pluses on this side. Now, finding the charges, liquid, the H2. So I have on this side, on the product side, 6 pluses and 1 minus. That makes it 5 pluses. So I have here 5 pluses versus 1 minus. So here's the higher side. I need to drop the 5 plus to 1 minus. If I add 5 electrons, I'll drop the 5 to 0, to neutral. So I need to add 6 electrons. Like this, I will take the charge to 1 minus. So we add 6 electrons on the higher side plus 6 electrons. And now this is the oxidation. The oxidation, I have 6 electrons lost, and the reduction, I have 1 electron gained. So we multiply the reduction by 6 and we add them up. So 6NO3 minus 6 times 2, 12H plus, I minus, and 3H2O liquid, giving 6NO2 gas and 6H2O liquid, and IO3 minus and 6H plus. Now H pluses on both sides will be cancelled. So 6H plus will remain here. And 6H2O and 3H2O, I have 3H2O that will remain on this side. So I'm gonna copy the rest. 6NO2 gas and IO3 minus, and iodide, aqueous and nitrate ion. That's it. These questions of oxidation number, you really need to practice the oxidation number so that it make the calculations and the balancing easy. So what's the oxidation of manganese? Since MnO2 is neutral, it means that the number of positive charges in it are equal to the negative. I have twice the oxygen. Each oxygen is -2. So what should be the charge of manganese to have a neutral substance? It is 4. Now, is oxidized in the following reaction? Okay, so question 2, 3, and 4 are related. So let me just find the oxidation numbers of each one. So here I have H, we add it in the acidic medium. H plus and H2O can't be oxidized and reduced because we add them when we do the balancing. So here we go. Let's look at the CR. The CR oxidation number is +3. What was it before? So I'm going to consider the oxidation number of one CR to be X. So I'm going to solve this in this way. 2X, because I have here 2, plus 7 times the oxidation number of O2 equal to the overall charge of the polyatomic ion. So 2X equal -2 plus 14. 2X is 12, X is +6. So CR was +6 and now it turned to +3. So CR got reduced to 3 plus. So this undergoes a reduction and it is the oxidizing agent. Whereas the other substance, the S2O3, is the one that is going to be oxidized. So this is going to undergo an oxidation, and this is the one that I call reducing agent. So in this one, this is the reducing agent, obviously. This is the here. Which one is oxidized? This one got oxidized. Which one is the reducing agent? This is the reducing agent, S2O3 minus. And the third question, in case they ask about the oxidizing agent, we can also say that Cr2O72 minus is the oxidizing agent. But it's not given here, the question. Now, how many electrons will appear when we are balancing this one? So, we balance S, 2S and 4S, so that's why they added the 2 to balance S atoms. And then 6O, and this becomes 6O, 2 times 3, 6O, O is balanced. So now when we look at the charges, I have here on this side 4 minus. Why is that? I'm just going to simplify it for you. We have 2 of this, it means SO3, 2 minus, twice. So the total charge is 4 minus. Whereas over here, the total charge is 2 negative. And I am telling you, in the steps of balancing, you balance the charge by adding electrons on the higher side of charge. So 2 minus is higher than 4 minus. I need to drop the 2 to 4 minus. So we need to add 2 more electrons. So 2 more electrons are going to appear on this side. Next, which element is reduced? I'm gonna go back to this question. When we did the calculations of Cr2O7, it was plus 6 turning to plus 3. So whenever Cr2O7 2 minus changes to Cr3 plus, it is undergoing a reduction. So this is the one getting reduced. If this is the one getting reduced, then the Fe2 plus is the one getting oxidized. So which element is oxidized? Again, I'm gonna use the same information. Whenever Cr2O7 minus changes to Cr3 plus, it is undergoing a reduction, and it is an oxidizing agent. So let's see now in this question. Again, I have this changing to Cr3 plus. I'm sorry. So this one undergoes a reduction. So this one is the oxidizing agent, whereas this one is undergoing an oxidation, and Ni is the reducing agent. I'm sorry. Now next, what's the oxidation number of H2O2? This is an exception to oxygen atoms. O is always -2 in compounds, except in hydrogen peroxide. In peroxides, O is not -2, it is -1. That's an exception rule that you need to be aware of. Now, what's the coefficient of the Fe3 plus in the following equation when it is balanced in the basic medium? So, let's first, this is a long process, so we need to split. So I'm going to split Fe3 plus into Fe2 plus. And quickly I'm gonna add 1 electron to drop the 3 charge to 2 plus. There's no way, no need to think about the H and the O since I don't have them in the equation. Cn minus into CnO minus. I need to add 1 oxygen here and I need to balance it with 2 hydrogen plus on the side. Therefore, 1 minus and 2 plus, that's a 1 plus on this side versus 1 minus on this side. So 1 plus versus 1 minus. The higher side is this one, and I need to drop the charge from 1 plus to 1 minus. Adding 2 electrons will do that. So I'm going to add 2 electrons on this side. And therefore, I need to multiply this equation by 2 in order to balance it. So this is going to be 2Fe3 plus Cn minus and H2O giving Fe2 plus and, giving 2Fe2 plus CnO minus and 2H plus. However, this question says that we need it in the basic solution. It's not going to change our answer because when we balance in basic solutions, we only look at the number of H plus on the equation, and that is not going to affect the coefficient of Fe. So the answer is 2. Again, what is the oxidation number of Br and BrO minus? So I'm going to put the BrO minus over here, and I'm going to consider this to be X because I don't know it. Oxygen is always -2, and the overall charge of this polyatomic ion is 1 minus, or -1. So X is -1 plus 2. X is going to be +1. It is C. So be careful to this question, and the answer key, it's wrong. It's C, not E. Now, which element is reduced in the equation below? Again, I just need to solve only one side of it and I can guess the rest. I charge was 1 minus and it increased to 0. So I minus got oxidized. Therefore, Mn is the one reduced. So the answer is A. Now, moving to more questions related to your quiz as well. In a voltaic cell, this is very important. You need to know these information. Electrons, they always flow from the anode towards the cathode because it's the anode that loses electrons and send it to the cathode through the electrical wires. So the electrons, the answer is C. The electrode where reduction occurs is called the cathode. That is a false statement. Okay, now the salt bridge. That's a very important question. In a galvanic or in a galvanic cell, we cannot construct a galvanic cell without the salt bridge. It's very important, and it's called a salt bridge. So it needs to contain a salt because the purpose of the salt bridge is to maintain and balance the electrical neutrality in the half cells. And I'm going to explain it again over here. So suppose I have these two half cells. So let's say solution of copper sulfate and solution of zinc nitrate. I have a zinc electrode and I have a copper electrode. And these two are connected by wires. And they need, of course, to have the electrodes, they need to be immersed in solutions. And they need to be connected by a salt bridge. Now, what's going on between zinc and copper? Zinc always operating at the anode because it's the one that is the weaker. It's as an oxidizing agent, it's weaker than copper. Copper is a stronger oxidizing agent. So zinc is gonna be the anode, while copper is going to be the cathode. Think about it this way. Zinc is going to be oxidized into Zn2 plus and 2 electrons. So there will be a supply of positive charges inside this medium. And the electrons are going to leave the zinc anode and they're going to go toward the solution over here. And these electrons are going to be catched by the copper ions in order to be reduced. So therefore, we have a consumption of positive ions. And on this side of the half cell, since the charges of Cu2 plus were equal, balanced by the charges of SO4 minus, now we are losing the Cu2 plus. So we have an increase in the amount of negative ions on this side. So what's going to happen is that the salt bridge here is going to play an important role. Since we have a consumption of consumed positive charges, the salt bridge is going, so let's say the salt bridge is K plus and Cl minus. So it's going to send the K plus towards this side of the cell to balance the positive and the negative charges. And it's going to send the negative ions to this side to balance the positive and negative charges. And always memorize it this way. The salt bridge will send the negative ions toward the anode and the positive ion towards the cathode. So a cell without a salt bridge will give you a 0 voltage. Also, what if you replace the salt bridge with just metal? Again, as if you removed it. So again, the voltage is going to be 0. So the salt bridge is very important. It maintains the electrical neutrality in the two sets. The balanced half reaction in which sulfate ions is reduced to sulfite. Sulfate ions reduced to sulfite. How many electrons? Okay, so let's do it. S and S are balanced. I need one oxygen on this side. So that means I will add 2 H pluses on this side. Now 2 pluses and 2 minus. This side has a neutral charge, whereas this one remains 2 minus. So we need to add 2 electrons in here in order to balance the charges. So it's a 2 electron process. Now the balanced half reaction in which chlorine gas, I'll tell you these questions, if they are given, the formulas will be given to you. Chlorine changed to chloride. First, I need to balance the atom, Cl. Be careful to this step. And now 2 minus versus 0 charge, so we add 2 electrons on this side. Next, which transformation could take place at the cathode? I need to look for the reduction, because at the cathode I have a reduction half equation. So what you need to do, you need to compare the oxidation numbers before and after and see which substance got reduced in the oxidation number. So O is always minus 2, H is plus 1. O is minus 2, H is plus 1. I can do this minus 2, minus 2. So you get my point. Now, let me just finish one by one. Here, N is going to be plus 2 because NO is neutral. So if O minus 2, then definitely N should be plus 2. And in this one, I have plus 1 for hydrogen. I don't know the n, and I have 2 of O2, so that is going to be minus 4 equals 0. So x is minus 3, it's plus 3. So from 2 to 3, it got oxidized anode. Next, Br2 is 0, and BrO minus, we just did it a while ago. If O is minus 2, Br has to be plus 1 to maintain the final charge of this formula to be minus 1. So that is an oxidation. It's anode again. Now, let's do the third one. The third one, I have H positive 1, S I don't know it, and 4 oxygen, that is 2 minus 2 multiplied by 4, that is minus 8 equal negative 1. So x minus 7 equal negative 1, x is positive 6. So S here, positive 6. Now, in the other change into H2SO3, I have H2 positive 1 twice, so that's a positive 2, plus S, that is X, I don't know it. And I have 3 times the O, so I have minus 6 equals 0. So X is positive 4. That is the one that got reduced from the 6 to the 4. Now, in a voltaic cell, again, electrons flow from anode to cathode. Now, which one is balanced at the cathode? At the cathode, I have a reduction. So it can't be Fe because Fe got oxidized. So to be cancelled. Now, what is the change? It's MnO4 to Mn2 plus. Now, if we look at, we just need to check the balancing of this one and see if it is correct. So, I have this one, the first one, because I have 8 H's and I have 8 H's. Look at the mistake here. I have 6 hydrogen atoms, where here it's written 12. So A is the right one. To gain an electron, an element must get reduced, and I call it oxidizing agent. The gain of electron by an element, it's a reduction. Moving on, what would be the coefficient of permanganate ion when the following equation is balanced? Permanganate ion is MnO4 minus. So what should be the coefficient? Okay, so there's a mistake in writing this one. It's Br2. So it is MnO4 minus going to Mn2 plus. That is 4H2O. That is 8H plus. And a 5 electrons on this side. Okay. And there's Br minus going to Br2. Since I have 2 Br, so I need to multiply this by 2 and add 2 electrons over here. In order to balance these two equations, I'm going to multiply this by 5 and I'm going to multiply this by 2. So obviously I am going to multiply this by 2. Again, here we need to work out the charges, which transformation could take place at the anode of an electrochemical cell. I need to find the oxidation. Which one charge will increase? This is 0 to minus 1. This is 0 to minus 2. This is positive 3 to 0. Reduction. This one, I have CrO2 to minus going to Cr2 plus. So I'm going to call this X, and 4 negatives equal -2. So X is -2 plus 4. That is going to be +2. Oh, well, we don't have any transformation over here. None of the above. So I'm gonna skip these questions because it keeps on repeating. Oxidation occur at the anode. Here you just need to find which one is a redox equation, reaction. You just have to witness in which equation I have a change in the oxidation states. This is just exchange of electrons. Nothing is happening. So A is not a redox. Same thing, 2 plus, and Pb is 2 plus over here. Br is minus, and Br and a compound is minus. So the only change occurring is in C. Now I'm gonna move on to the final part of this worksheet. Oxidation always occur at the anode. Never forget this. And electrons, they flow from anode towards the cathode. And the purpose of the salt bridge is to maintain the electrical neutrality of the cell. It has to balance the charges. Now, which of the following is a true statement? When I have an equation like this, I need to look at the charges, at the oxidation states. I have an increase in the oxidation number of aluminium. So this aluminium is the anode that undergoes an oxidation because the oxidation number increased. And the Cu is the cathode. So electrons are going to flow from aluminium, from anode to cathode. So it is 1 and 4. Which of the following is true for a voltaic cell? A voltaic cell converts chemical energy to electrical energy. So A is for an electrolytic cell. Reduction never occurs at the anode. It operates according to a spontaneous redox reaction. Yes, a voltaic cell versus electrolytic cell. This is a non-spontaneous cell. This is a spontaneous cell. This one will have a delta G negative and a K above 1. This will have a delta G of positive and a K less than 1. The voltage here, the E cell, is going to be positive, whereas the voltage here will be negative. Now, I'm going to move on to these questions of balancing. I'm going to skip this because I already did a similar one. Now, pay attention to this one over here in acidic medium. So I'm going to split the two equations, 1V, 1V. 2O, so I'm going to add 2H2O on this side. Now makes it 4 hydrogens, so I'm going to balance H by adding H plus. Now let's count the charges. I have 3 plus on this side, and I have 5 plus on this side. So this is the higher side. I'm going to add 2 electrons to drop the 5 to 3. The next one is Sn2 plus to Sn4 plus. Everything is balanced. We only need to add electrons in order to balance it. Finish. That's it. We are going to add these two equations together. Okay, Now another example, be careful to those atoms, formulas. So again, VO2 plus to V plus, I'm just gonna copy it again because I just did it in the previous step. Plus 4H plus, giving 2H2O and V3 plus. Now, Cl minus into Cl2. First, start balancing the atoms by adding coefficients. And that's it, there's no O and H in it. Now I'm gonna add 2 electrons on this side. And I think I forgot to add 2 electrons of this one. So 2 electrons cancel out, so we just add it, and the balancing is very simple. Finally, this question, and we reach the end of our revision. I have a galvanic cell. Now, there is no indication on the diagram to help me guess which one is the anode and which one is the cathode. So I'm gonna use the help of the standard potential reduction of these half cells. Now this is negative 76.76 and this is negative 0.91. The half cell that has the stronger oxidizing agent is the one that is going to undergo a reduction and the one that's going to be on the cathode. So this is the one that has a higher value. So this is the zinc 2 plus that is a stronger oxidizing agent than Cr2 plus. So therefore, this is going to be on the cathode undergoing a reduction, and this is going to be on the anode undergoing an oxidation. So the anode is Cr. Never mention Cr2 plus to be an anode because anode are metals. Write the balanced redox equation. Zn2 plus is going to be the cathode, whereas the anode, I'm gonna see an oxidation half equation. So adding these two together, I'm gonna get zinc 2 plus and Cr, giving Zn and Cr2 plus. We need to add the physical states. Never forget these. Indicate the direction of electron flows. Since now we know that this is the cathode and this is the anode, electrons are going to go in this direction. So that's the flow of electrons. And another question, the salt bridge is filled with K plus and Cl minus. Where are the Cl minus going to migrate? So in this equation, I have toward the cathode, in the cathode, I have a consumption of positive ions. So the positive K plus are going to come on this side, whereas the negative chloride ion are going to come on this side. So on the diagram, you can indicate the migration of Cl minus. And that's it. Thank you for listening.